Right, part 2. Just to finish up what we were doing earlier and have a look at a problem that involves using the cosine rule, and highlights another thing about these ratios, that there's two angles that can have the same sine or cosine in 360 degrees. So you have to be a bit careful with that. Okay. So in a problem like this one here, been given all three sides and asked to solve it. In this case, probably the best way to tackle it is to find the largest angle first. And in this case, the largest angle is going to be opposite the longest side. So the longest side here is A. Yeah, and we've been given all three sides. So if we go back to our methods on that page, when we're given all three sides, we can't use the sine rule because we don't know any angles. So we've got to use the cosine rule. And we're going to use the cosine rule that involves the side A. So it's going to be the version A squared is equal to B squared plus C squared minus 2BC cos A. Yep. Now we've got a rearranging job because we want to find the angle A. Where are we going to start with that? Where would you start? Bear in mind, we could lump that into one and say that's all one big number. Because that's the cosine of A, that's 2 times B times C, which are constants. So that is a number. Jake, why have you got to divide? How is that attached to those two things? Plus, minus. So what's the opposite of minus? Plus. So we're going to add, a suggestion is to add that bit to both sides. That means that will cancel that out, and that will get cos A over that side, and it will have it positive. The problem with dividing by cosine of A is you'll do this, right? But you've also got to divide that by the cosine of A and that. So you're compounding the problem. Okay? Usually, with rearranging, you've got to work with BODMAS in the reverse order. Get rid of subtraction and addition first, and then get rid of the brackets. Not always, but usually. So we're going to add 2BC cos A to both sides. We're going to get 2BC cos of A is plus A squared is equal to B squared plus C squared. Anybody didn't follow that? I've just taken that constant because that's all it is. It's a number. We don't know how big it is, but it's just one number. Shifted it all in one go. And I'll write that there. I've added to both sides. So effectively, on this side that cancels out. What's the next thing to do? Remembering that we want eventually to get cos A on its own so we can find the angle. Yes, subtract a squared from both sides. So we got cos A oh sorry, 2bc cos A, 2bc cos A is equal to b squared plus c squared minus a squared. Next bit, divide by 2bc. Yeah, well done. Divide by 2bc. We get cos of A is equal to b squared plus c squared minus a squared all over, which implies brackets, 2bc. Then we can just use the inverse cosine function. So we can say the angle A is equal to cos to the minus 1 of all of that. B squared plus C squared minus A squared all over 2bc. And then we can put our numbers in. So it equals cos to the minus 1 brackets. Side B is 7.5 centimeters plus side C 6.5 centimeters squared minus side A 9 centimeters squared all over 2 times B 7.5 times C, which was 6.5. Push the buttons. What do we get? Yep. Actually, he's got 79.66 in here. Brackets. Do you know where you went wrong with the pushing the buttons? Okay. Yep. All right. What you can, how would you then? And I'm not proposing to go through all of finding the other angles, but how would you propose about going through that? You can kind of do that to finish this off during the week. So you could, yeah, if you go to sine rule now, right? The only issue with going to sine rule now is that you're going to use that angle that you've calculated and rounded, right? But what you can do, an option, is to carry that result through to that calculation. I don't know if you can get that in fractional form. No, it won't go into fractional form. But you could, that's possible to carry that result through. If you're concerned about the error there, you could use the cosine rule again and just change the rearrangement so that you used all three sides again. Okay, I don't know what he does in here. He does apply the sine rule and uses that method, and you wouldn't be very far out. I'll tell you what you're heading for the other two angles. You can jot them down. I'm just going to go through the calculating of the area. It's got angle B as 55.06 degrees, and angle C is 45.28 degrees. B was 55.06 degrees. And a check of that would be to add them all together. They should equal more or less 180, shouldn't they? What I want to do is the area using the three sides. Because what we're going to do is first find circumference, that's not the circumference. First find S. S is equal to A plus B plus C, the three sides added up. So that's 6.5 plus 7.5 plus 9. It's 1423. Yeah. Oh no, we've got to divide that by 2, haven't we? Over 2. So that's all of that over 2. The result of that is 11.5 centimetres. So it's half the perimeter. Then what we can do is say that the area is equal to the square root of S times S minus A times S minus B times S minus C. So that's the formula. So we can put the numbers in. 11.5 times 11.5 minus A times 11.5 minus B, 7.5 times 11.5 minus C, which is 6.5. Again, do that all in one go, push the buttons and see what result you get. So using that formula, knowing the three sides, we can find that. We could check it with any one of the other formulas for finding an area. Right? So you could get a problem requiring you to do that, and you actually could, going back to that problem we worked through, you could use the sine and cosine rules as a way of solving that. Because if we look at this, we got two angles. So it might be possible to solve that by using the sine or cosine rule rather than creating the two formulas involving h and x. Okay? There might even be one like that in your extra work this week at the end. What I want to do now is move on again just a little bit. That is into wave functions. So related to the sine and cosine that we've already done, but repeating waves, sine wave and cosine wave. If we look at the in terms of sine from 0 degrees around, and we graph that on a linear axis, of degrees on the x-axis, height of this position here on the y-axis. For sine, we get a sine wave that starts at 0, peaks at 1 there, goes through 0 again, goes through a negative peak, and back to 0 at 360 degrees. Equally, we could have our angles in pi radians, 2 pi radians, 90 degrees as pi over 2, and 270 degrees as 3 pi over 2. Sorry? The y-axis is the length of this line as it goes round the circle. So what you're doing is that in each angle position you project across, yeah, and then when you join the dots up, you get the sine wave. You ever seen that children's toy called spirograph, where you put a pen in a cog and wind it around? Effectively, you're drawing sine waves. Yeah, when I was a boy, back in the day. You know what I'm talking about, Paul, though, do you? Yeah. Yeah, just wind it round. That make pretty patterns. Cosine, so the sine of 0 is 0. The cosine of 0 is 1. Therefore, the cosine starts at a peak, goes through 0 at 90 degrees, has a negative peak at 180, back through 0 at 270, and then peaks again at 360. But they're repeating waveforms. Okay? That's the shape of the AC mains waveform that comes out of these sockets in this room, because that waveform's created using a generator that turns around in a circle. That's where it comes from. So these wave shapes for you ain't going to go away, particularly the sine wave. Okay? They both repeat every 360 degrees, if they're the same frequency, or every 2 pi radians. Yeah. So, what's more important to me is to get across to you, certainly for the electrical part of this qualification, is the form of the sine function that is A times the sine of omega t plus or minus alpha. So we need to be familiar with that form of a sine wave. We've introduced, so I've made it here nice and big. The A in front of the sine signifies the amplitude of that waveform. That is the peak value. So when in the original one, in this one, it was just sine of the angle, there was nothing in front of it, so it peaked at 1. If we made A 2, then the peak of that waveform would go up to 2, and I'm going to show you that in a minute anyway. So the A in front is the maximum. So that could be the maximum current for a current sine wave, could be the maximum voltage for a voltage sine wave. Okay? You could also come across this in oscillating machines, in mechanical as well. So that you're going to get a cam going up and down because that's up against something that's going round and round and so on. Okay? Or linkages. Then we got the sine function, we got brackets. Then we got omega. Okay? Omega is the angular velocity of the sine wave going round in an anti-clockwise direction, and it's measured in radians per second. So now, religiously, we're all going to put our calculators into radian mode. As soon as you've got omega, go rad. Right? As soon as you see omega, go rad. I've got 3 calculators now, I only had 2 a minute ago. Probably, do you know which one's yours? This one? Alright. So we got omega, that is not W, is the Greek letter omega, okay, and it's the angular velocity. Then we've got time in seconds, and then we've got a plus or a minus, and we got alpha. Alpha is the phase angle relative to 0, so it can be a positive or negative from 0 in radians. And I'm going to go through each of those parts in turn. But always remember, it's a little bit small on there, if you see omega, omega always equals 2 pi times the frequency, where f is in hertz, or cycles per second, as our American friends used to call it. Hertz. Okay? And then we can get the period of the waveform, the time it takes to go from there to there is the period t. And that comes from t is equal to 2 pi over omega. T is also equal to 1 over the frequency in hertz. That will give you the time it takes for 1 cycle in seconds. All reasonably happy with that, and I'm going to go through each bit one at a time now and show you the difference it makes when you change them. So if we look at this diagram, okay, what I've done is put 3 sine waves of different amplitudes on to that. I've used autograph. The blue one, there's nothing in front of the sine, therefore it's 1 times the sine of t, so it goes up to 1. Then I've got 2 sine t, peaks at 2, negative peak at negative 2 as well, and then 3 sine t is a peak at 3 and a negative peak at minus 3. So that's showing you how the constant in front of the sine function determines what the peak of the waveform is. Next, frequency. If I've got omega is equal to 1, we complete this cycle here from there to there in 6 point some odd, that's 2 pi radians. Yeah. If I make omega 2, we get 2 cycles in the same distance, twice the frequency. If I made omega 3, we'd fit 3 sine waves between there and there, and so on. So if there's a multiple of omega, it's omega that's controlling how many sine waves you get in 1 time period, or the time period of 1 sine wave. You can think of it in either way. But the value of omega, and its constant in front of it, controls the frequency, or how many cycles we get per second, or the period. It's all controlled by omega and what it's multiplied by. Probably the most difficult one to get correct is phase shift. Okay? If I have f of t is 2 sine t, so the peak is 2, omega is 1, okay? There is no plus or minus any phase angle. So that's the red one starting at time is equal to 0. The blue one has a positive alpha. What that means is it's got a phase shift of plus pi over 4 radians. It starts pi over 4 radians. So if I extended that down, that in there is pi over 4 radians. That distance in there. It's a head-in time of the red one. We only need to consider phase angle when we're looking at two waveforms that aren't in phase with each other. It means at time equals 0, this waveform has already got some amplitude to it, because it's ahead of, it's peaking sooner than the red one. We'd say it is leading, because it is ahead of the red. It's leading the red one. The purple or pinky colour one, whichever way you want to look at it, has got minus 24, minus pi over 4 radians. So it's peaking pi over 4 radians, or it crosses 0, pi over 4 radians after the red one. It is lagging the red waveform. It's terminology used in electrical. So the blue one leads the red one by pi over 4 radians. The pink one lags the red one by pi over 4 radians. Yeah. And as those, or that, those that were with me for science last year will testify that we will come back to this, no doubt, in semester 2. And we'll be doing this in level 5 electrical principles for sure. Okay, so these waveforms and phase shift and positive and negative, lead and lagging, ain't going to go away. So, an alternating current is given by R is equal to 30 times the sine brackets 100 pi t plus 0.27 amps. Notice that this is a lowercase I. Very important. It means the instantaneous value at a given time t will be found via that function. This one is the peak amplitude. So it says find the amplitude. It's 30 amps. You just pull it out of the equation. You know that this is in the form of I is equal to the amplitude sine omega t plus or minus alpha. That's the form it's in. So if you're given this in the exam, I'd probably expect you to make that statement. Yeah, that you know that's in that form, and therefore the amplitude A is simply 30 amps. You just pull a number out of that equation, there it is. The period, frequency, and the phase angle in degrees and minutes. how can I get the period here? And more importantly, how can I get the frequency? Well, how can I draw that out of that formula? Which bit is related to the frequency in hertz? Omega is equal to 100 pi. Pulled out of the question. Remember, this bit is omega t. That bit there is omega t. So omega must be 100 pi. Get rid of the t. Yeah. Omega is also equal to 2 pi times the frequency f. So we can rearrange that for f now, can't we? What is f equal to? Rearrange that for f. What we got to do? Tell me how you get with that, Paul. That's 2 times pi times f. So if we're multiplied, how do we get that over the other side? We've got to divide. So as f is equal to omega divided by 2 pi. That's 100 pi. Remember what I said about pi's cancelling each other out? There you go. 2 pi's cancel out. 100 over 2 is 50 hertz. So quite often, I told you, pi cancels out. There's a prime example. No need to evaluate it. Period t is equal to 1 over f. So reciprocal of the frequency, 1 over 50 equals 0.02. Dom, anything else you want to give me there? Seconds equals 20 milliseconds. But either would be correct, and you get full marks in the exam for either of those two answers, 0.02 or 20 milliseconds. And then last but not least, phase angle in degrees and minutes. Alpha has been given to you as 0.27. So earlier we went through how to convert that into degrees and minutes. I'll leave you with that. So that comes out at 15 degrees 28 minutes. But tell me, is it leading or lagging? Look back at the notes if you don't remember. Look at the function that you've been given for I. So plus 0.27 radians. Where we had a plus pi over 4 radians, it was a leading. So a positive angle means it's a leading situation. Okay? And you should really be qualifying that with that type of thing. Is it leading or lagging? Yeah? Could be either. Another problem. An oscillating mechanism has a maximum displacement of 2.5 meters and a frequency of 60 hertz. At time t equals 0, the displacement is 90 centimetres. Express the displacement in the general form A sine omega t plus or minus alpha. How can we go about doing that? Form is A sine omega t plus or minus phase shift. Yeah. What's the easiest thing to get out of there? Even easier than that. Time will remain as t. Amplitude. A is equal to max displacement, which is equal to 2.5 meters. Yep, everyone happy with that? Next bit. Remember, we want the frequency in omega t form, don't we? So we want omega is equal to 2 pi f. Yep. So it's 2 pi times the frequency 60 equals no calculators needed. Do not evaluate pi here. $120 pi. We can start to build our formula up here. Displacement is equal to 1.2 sine. We've now got omega. It's 120 pi t plus or minus something. Is it going to be a positive or negative phase angle in this case? Oh, sorry, 2.5 meters. That's what we got so far. Is that going to be a positive or a negative phase angle? Yeah. Agreed? So how are we going to find out what this phase shift is? How can we do that? We've been given the information that the displacement equals 0.9 meters when t equals 0. Yeah? So we can put that fact into the formula. 0.9 is equal to 2.5 sine 120 pi t plus the phase angle. Yeah? And what's this bit when time is equal to nothing? So it's just the sine of the angle alpha. Yep. Now can we rearrange that so that we can find the angle alpha? How do I rearrange that so I got alpha on its own? Or even the sine of alpha on its own? Take away 2.5. How is the 2.5 attached to the sine of alpha? By multiplication, isn't it? It's 2.5 times. So what do we do to get rid of multiplication? Divide. So it's 0.9 over 2.5. So the angle alpha is the inverse sine of 0.9 over 2.5 equals whatever that come out to. Your calculator should be in radians, so you should get your answer in radians. .37. Yeah, I'll go with that. So the full formula or function is displacement equals 2.5 sine of 120 pi t plus 0.37. And if you plug 2.5 times the sine of 0.37 in your calculator, you should get approximately 90, because that's the displacement at t equals 0. Yep. Yeah, 2.5 times the sine of 0.37, because that will cancel if t is nothing, and you should get around about 90, allowing for your rounding errors. .904, 90 centimetres in other words. 0.9 of a metre. Yep. Happy? Everyone happy with that? No. Who's shaking his head? Paul. If t is nothing, that bit disappears, doesn't it? Yeah. Yeah, 0.37 in the sine function. 2.5 times sine of 0.37, you should get 0.90 and some odd. Yeah, because that's your rounding errors on the angle in radians. Okay? Everyone happy with that? Right? It's about breaking the problem down, and this is about understanding that standard form of the sine wave. Amplitude times the sine of a frequency in omega t plus or minus the phase angle alpha. You need to understand that form, what each part of it is and does. The displacement at time is equal to 0 is 0.9. The displacement at any time can be found using that function. Yep. Yeah, the question was asking you to produce that function from the data given, wasn't it? Express the displacement in the general form. Right. instantaneous value of voltage in an AC circuit at any time t is given by that. Yeah. V is equal to 340 sine 50 pi t minus 0.541 volts. Leading or lagging? Negative angle means lagging, right? So immediately now it's lagging. But the question says determine the amplitude. Amplitude is, right? So A, you put in form of V is equal to A sine omega t. Amplitude is equal to A, which is equal to 340 volts. So if you're given a question like this, you might get 2 marks just for doing that. But you need to know that that number in front of the sine function is the amplitude. How can I find the periodic time and frequency? Yeah, but how can I get F? We need omega, don't we? What is omega in this case? 50 pi. Therefore, what do we also know about omega? 2 pi f. Therefore, f is equal to 50 pi over 2 pi equals 25 pi hertz. No, it ain't 25 pi, is it? It's just 25, because the pi's cancel each other out. 25 hertz. So we've got the frequency. Period is how do we find the period? 1 over frequency, 1 over f, 1 over 25. Or 40 milliseconds. Yep. Anything else in part A? Phase angle in degrees. Alpha is equal to minus 0.541 volts. 41 rad, sorry. Therefore, alpha equals pi over 180 times minus 0.541 equals Have I got that right? No, is it 180 over pi, isn't it? I got that the wrong way up, haven't I? That bit gives you how many degrees is 1 radian, then you multiply it by the number of radians to get the answer. Minus 31 degrees to minus 30.997. Which would round to 31.0 to 3 significant figures. All agree with that? Yeah? So that's done part A, and that was no more than we'd done before, really. The value of voltage when T is equal to 0. So if we take that function and we say V is equal to, and that was 340 times the sine, and when T is equal to 0, what's the omega T bit equal to? So it's just the angle minus 0.541 radians. Plug that in the calculator. Answer is
negative 175.1.
Yep. Volts. I agree with it. Everyone else agree with that? Yep. Then it says find V. So that is B. C says find V when time is equal to 10 milliseconds. So we got to do a little V 340 times the sine of, open the brackets, 50 pi times 0.01 for the 10 milliseconds minus the angle 0.541 radians. Again, plug that into the calculator. Shouldn't have any problems at all getting the answer. .4 volts. .5 if you prefer. Okay. D is find time when V is equal to 200 volts. This is where this question gets different to what we've done before, because we got a formula that says V is equal to 340 sine of 50 pi t minus alpha. I'm just going to use that for the minute. Okay, I'm going to leave that as that. We want to find t. Yeah? Let's replace this with the number 200. We want to find out when that equals 200. No, remember the brackets here are that in there is a number that you're taking the sine of. Yeah? So it's not quite the same as having x plus 3 in brackets. Right? What we do here is get rid of the 340 first. So divide by 340. So we go 200 over 340 is equal to the sine of 50 pi t minus the angle. How can I get rid of the sine function on this right hand side? Take the sine to the minus 1 of both sides. That's what I'm going to do. That's what I did there. So I'm going to go sine to the minus 1 of 200 over 340. That then sine and the brackets disappear on this side. 50 pi t minus the angle alpha. How do I get alpha over that side? Add it. So I'm going to plus alpha to both sides.
So you say it's alpha 31 degrees?
Yeah. Well, or minus 5, whatever it is, radians. While I'm rearranging, this is a personal preference, but while I'm rearranging, I'd rather leave that as alpha. There's less chance of me missing one of the digits off or getting it wrong as I'm moving things around if I leave it as alpha. Yeah? I can always write the actual number in afterwards. So, sine to the minus 1 of 200 over 340 minus alpha is equal to 50 pi plus, sorry, adding. We're starting to get somewhere now. What can we do to this side to make it t on its own? We're going to divide by 50 pi. And I'm going to be blinking awkward and I'm going to write t on this side. And it's equal to the sine to the minus 1 of 200. Border's getting on my nerves. Sine to the minus 1, 200 over 340 plus alpha all over 50 pi. And now I can put all the numbers in. T is equal to sine to the minus 1, 200 over 340 minus, because the angle given as a negative angle, it's like plus minus, so it becomes a minus 0.541 radians. Notice I'm using the given angle in radians, not the calculated 31 degrees, which is rounded. It's plus, right? Okay, I'll do it. It's plus, but the angle you're adding is a negative one. Let's do it. It's plus minus 0.541 radians. Yep. So that those two overall make a negative. But do it that way if you wish. Over 50 pi. I don't mind. If it helps you to understand, if you'd rather put the positive sign in, but you must not drop that negative off the given angle. Think what Mr. Bird get? He gets 7.447 milliseconds. This week's stuff is there's some further practice on right angle triangle trigonometry. I wouldn't think as far as the trig go that you need to do too much with that. You'll find more problems in the Bird book if you need them. Another problem involving right angle triangle trigonometry, similar to the one we had a look at moving forward a little bit and using the two, coming up with the two formulas and rearranging. That'd be a good one to practice. Can you have another go at rearranging that formula with two variables in it and cancelling one of them out? So using the factorisation to get the one lot of x and solving that problem. There's further practice on the sine and cosine rules with a problem involving sine and cosine rules, okay, and further wave function problems there and there. And those bits over there are the final answers you're heading for. So that's what you should be getting. And then next week, complex numbers in polar and rectangular forms, and what you're looking at if you've got the 7th edition and you've got the time to look ahead is chapter 33.
Where you have two and then your times in.
That's where you have, yeah, you've got the polar form, magnitude plus or minus the angle, and then you've got your rectangular form, which is in phase component plus or minus a number times j, with j being equal to, anyone in the room? Square root of -1. Yeah. Hold done. It's an abstract thing because we can't have the square root of -1, so let's call it j. If I was a pure mathematician, I'd call it I, because that's what, but the engineers can't use I, they use j. All right.